Good. How are you?
Professor, for your finite element class, you'll be going on talking more about the midterm about the week.
Probably next week.
Oh,
We'll
next
talk
week,
about
okay.
Yeah.
Yeah, I was assuming, yeah, since we haven't finished our midterm project,
Mhm.
we will talk, won't touch it as much.
Yeah. Because I wanted you guys just to focus on the project first, and then
Okay.
we'll talk about midterm after
It'll
that.
be closely related to the homework.
Oh yeah, it'll be basically the same.
Okay.
Yeah.
Cool, cool.
Hi, Professor. Would you be able to help me look at 2C? Just steer me in the right direction. I'm kind of struggling with the moment from the backpack.
Sure.
Let me.
Yeah, that one's a tough one. So I think I think like you said, the tricky part is the moment from the backpack. And so let me just kind of draw that one for you. Right, so let's say that this is the person's back, just like this. We have the angle theta. And I realized after talking to someone in office hours today, I was kind of missing a crucial piece of information. And so I think maybe this might help. And so we say that the backpack is at some location out here. Okay. And so the piece of information I'm missing from the homework is that this part, or this length right here where the backpack attaches to, this is the length of the entire back divided by 2. Right, so this length is LB divided by 2. I forgot what length I gave this one. I think it's like LP or something like that, right? Or LB. Right? LT. Okay.
Oh, yeah, that was LB, the whole length.
Oh, okay.
LB.
It was LB. Okay.
Yes.
Okay. Right. And so we want to find the moment of the backpack weight, right? And so the backpack weight is going to go straight down. So it's going to go just like that, right? Okay. And so since we have a vertical force here, the moment arm that we want is actually horizontal, right? And so it's purely just this distance right here. And so we need to use a little bit of trigonometry just to find out what this horizontal distance is. Okay? And so the way I kind of broke this down is that I kind of broke it down into 2 triangles. And so wait a second.
Yeah, the LT and LB switch.
Oh, LT, LP. Okay. Let me switch it. Thank you. So this is LT, this is LB. Yeah, okay, that makes sense. All right. And so the first triangle that I'm looking at is this one right here, right? Because we have this angle here. We know the length of this hypotenuse. The length of this hypotenuse is LT divided by 2. And so this horizontal distance is simply just going to be LT divided by 2 times cosine of theta, right? Okay. And so that's that distance. Okay. The other triangle that you can draw is actually one that involves this length right here. Okay. And I think this is the part that's tripping everyone up. So we basically want to break up this LB into a horizontal component and a vertical component, right? And so we're going to make one length like this, and then another length just like that. Okay, so we make a right angle here. Okay. And the tricky part here is, how do we assign the angles for this triangle? And so it turns out, just due to geometry, this angle right here is the exact same angle as this angle theta right here, because this length right here is perpendicular to this one, right? And so when you make kind of a horizontal and vertical line, then the angle for that one is basically the same as that one, okay? And so now with this in mind, we can find out the horizontal length here, right? And so that horizontal length is going to be LB times sine theta, okay? Right? And so the total horizontal distance is going to be the difference between this guy and this guy. And so we have LT divided by 2 times cosine theta, okay, minus LB sine theta. And so depending on what the angle theta is there, you're going to get either a positive or a negative number for this. And so if you get a positive number, that means that the backpack, the moment is going to be on the right of the hip joint. Okay. Okay. Basically, whenever you compute lengths like this in a free body diagram, if you get a positive number, that means it's, the orientation is exactly as you drew it up. Okay. But if you get a negative number, that means that basically the distance between the hip joint and this vertical force is going to be on the opposite side. Okay. Okay. And it all depends on what the angle theta is. Okay. Right. And actually, the sign of this moment arm will also tell you whether the abdominal muscle is going to be acting or the back muscle is going to be acting. So a lot of it really depends on that angle theta, which is essentially your posture. Okay. Does that help you out a little bit?
Yeah, that really helped. Thank you so much.
Awesome. Great. Okay. All right. So for those of you just tuning in, this is just a little bit help on problem 2C on the homework. Okay. I know the geometry for that one's a little bit challenging, and so I thought someone asked, and so I thought I'd give some tips on that one. Okay. And so classes started, and so I can't go over this again, but because we got to get rolling on the other stuff. But if you want to see kind of the explanation behind this, it'll be on the recording, which will be up later today. Okay. All right. All right, and so let's come back here. Okay, so good afternoon, everyone. We are in our second lecture of week 11. So how's everyone doing today? Good. Right. Okay, and so we're continuing on with our discussion of dynamics. Okay, and so we're going to finish up linear dynamics today. We're doing that for sure today, and then we're going to start on rotational dynamics. Okay, so a little bit of a transition day today. Okay. All right. Quick question. So will we have research projects due while working on our main project? Probably not. And so, now that we've kind of entered into the end game of the class a little bit, or I guess after the midterm exam, it'll be really end game. I do want you to focus your research efforts on just the final project. And so, I do want to have one more homework assignment just because I want to make sure that you guys get some practice with the dynamic stuff. Also because the dynamic stuff is pretty cool in my opinion. And then we'll go from there. Can the homework be shorter? I'll try. So
Would those homework have the research portion or just like the solving?
it'll just have the solving portion. Yeah.
Conceptual? Okay.
Yeah. So right now my plan is to have just one more homework assignment for the class on the dynamic stuff. So on linear and rotational dynamics. And it won't have any research component for it. Yeah. And so it'll just have the problem solving. It's just like Squid Game. I see. Yeah. Yeah. And so, because, we are reaching the end of the semester, so I'll make the last homework assignment shorter than this one. Okay. Okay. Great. So are there any other questions I can answer before we get started for today? Okay. All right. So let's go ahead and get rolling. Okay, and so where we left off was we were talking about linear momentum and linear, and in particular, force impulse phenomena. Okay. All right. And so the idea with force impulse is that, if you want to change the momentum of an object, you have to apply a force on that object over a certain period of time. Okay. Yeah, so it can either be, you can either, completely change the direction that the object is moving, or you can even just slow it down or speed it up in the same direction, right? So any change in momentum is always going to occur as a result of a force acting on an object. Okay. All right, so the formula that we have is the following. And so we have the force that we apply multiplied by time, okay? And this is going to be the change in momentum of the object. And so it's going to be mv2 minus mv1. Okay. All right. And so with this formula, there's kind of two aspects of this formula that I want to highlight to you guys. Okay? And so basically, in order to make any significant changes in momentum, you have basically two levers that you can play with, or two degrees of freedom. Okay. Okay. And so the first option that we have is we can either just apply a really, really large force. Okay. And so, in that case, it doesn't matter all too much how much time that you apply it for. So if your force is sufficiently large, that's enough to cause a big change in momentum. Okay. Or another option is we can just apply a force over a really long period of time. Okay. And so we can either have F really big or T really big. Okay. Or you can have both really big, and that results in a big change in momentum. But just because of how this equation is structured, you can have one or the other. Okay. And so what's interesting about this is that the human body, or I should say your instincts, already understand this phenomenon really, really well. And so whenever you're faced with situations where you have to change your own body's momentum, your body has natural tendencies to do things that utilize this this equation actually really well. Okay. All right. And so let's talk about a couple examples on how this is and how the body actually uses this. Okay. So, question. So does an object translating across a weak adhesive count as applying a force over a long period of time? Yeah, it absolutely does. And by that same token, friction also accounts for that too. Friction and air resistance, right? Because if you take, it doesn't even matter how big of an object. And so let's say you pick a really big object and push it, across a floor that has some friction, right? Even if you give it like a really large velocity, eventually what you expect is that, that object is just going to slow down, right? And so what's happening there is that the relatively small frictional forces, or as you say, relatively small adhesive forces, because you apply that over a long period of time, that's enough to actually stop the momentum of the object. Yeah. And so it just takes a long time if you don't have a very large force. Mm-hmm. All right, and so the first example where the body makes use of this is, let's say that you want to, or you're in a situation where you want to jump, you need to jump as high as you can. Okay. And so if you think about it, so if you stand up from your seat right now and try to, if I told you to jump as high as you can, I think most people will crouch down as far as they can first, and then try to jump up from there. Okay. And so crouching down before you jump has a lot of benefits, and it's a situation that we've talked about before in this class before, right? Okay. And so on the one hand, we know that when we crouch down, we put a lot of stretch into our leg muscles, right? And so into our quadricep muscles, we stretch them out. And so we have the elastic properties of the muscle help us out with the jump, right? And so that's one good motivation why you would do that. But another motivation to do that is, you give your body more time to apply a force onto the ground, right? And so if you compare that to, maybe you just jump in place right now, right? And so the time in which the time between when your brain says to jump versus when you leave the ground is not very long, right? And so if you just jump up with your feet, there's not that much time to apply that force. But if you crouch all the way down, then the amount of time it takes when you initiate your jump to when you leave the ground is a lot longer, because you have to stand all the way up first and then you leave the ground after that. Okay. And so because you're applying a force over a longer period of time when you crouch all the way down, this helps you achieve a much higher vertical momentum, and helps you get much higher than before. Okay. And so that's one way that your body naturally utilizes this force momentum idea. Okay. All right. And so another example of this is the opposite situation. And so let's say that you're jumping down from a very large height. Okay. Okay. And so when you're jumping down from a very large height, I think the primary concern is that you hit the ground with such a big impact and you break all the legs in your legs, right? Break all the bones in your legs. Okay. And so what does your body do to help alleviate this? Okay. And so what your body does to alleviate this is that they, as well as we like to call it, we bend our legs to break the fall, right? And so, if you're coming down from a large height, you have a very large vertical momentum. Eventually, your body wants your vertical momentum to be 0, right? Because that's where you're stable on the ground. And so if you kind of jump down and you just keep your legs straight the whole time, or worse, you keep your legs locked, you're going to apply all that change of momentum over a very short period of time, right? And so the amount of time that the ground is, impacting your legs when they stay still, is very short. And so F is going to be really large. And when F is really large, then that's what can break your bones, right? But, if you bend your legs as you fall down, then you kind of distribute that force over a longer period of time. And so you can achieve basically the same change of momentum, but with a much smaller force, okay? And so that allows you to, jump down from or change your body's momentum really easily without risk of breaking the bones, okay? And actually, I want to do an example which shows, how much of an impact this makes. Mm-hmm.
Is that why cats can fall from such large heights?
It's part of the reason. Yeah, part of it is another. Yeah. So they're much cats are much smaller creatures, and so they have much less mass. But also just the design of their body is a lot different. They also have 4 legs too, and so with 4 legs, it's you spread the weight on twice as many legs.
Like when they land, their legs are able to flex really well.
Yes.
To absorb the impact.
Oh,
I'm
yeah.
sure it helps that they can provide that force there too.
Oh yeah. Yeah. All of those are good reasons. And actually, once we get to rotational motion, we'll actually talk a little bit about how cats actually always land on their feet too. So if you take your cat and you drop it, and I don't recommend this if you have a cat, but if they ever do fall, you'll notice that they always land on their feet. And so cats actually have a very instinctual understanding of rotational of angular momentum that allows them to do that. But we'll get to that in the next set of lecture notes. Okay. All right. Any questions on this before we move on to the example? Okay. All right. And so let's say that we have that exact situation that we just talked about. So let's say that we have someone who has a mass of 60 kilograms. Jumps down from a ledge that's 0.7 meters off the ground. Okay. All right, and so we're going to consider 2 situations for this, right? And so in one situation, he's going to keep his legs straight as he hits the ground. Okay. And in the other situation, he's going to bend his legs as he falls so that he breaks his fall. Okay. Okay. And so let's go ahead and draw this. And so in situation 1, so let's say that he keeps his legs relatively straight. Okay. Okay. And so in situation 1, let's say that the contact time, or the amount of time that he's contacting the ground, is about 0.2 seconds. Okay. Right. And so he basically, and so what I mean by contact time, because this is a very classical situation that's covered in a lot of physics classes. And I always had a hard time understanding, what they mean by contact time, right? Because if you're standing on the ground, the amount of time you're in contact with the ground is as long as you keep it there, right? And so when problems like this, like contact time, what they mean by this instead is that this is the amount of time it's going to take to basically kill all the momentum in the system. Okay. right? And so, when textbooks or physics textbooks say, contact time, what they really mean is, this is the amount of time it takes, to reduce momentum to 0, okay? And so basically, for this problem, what we mean to say is that, when this person jumps off the ledge, okay, he's going to have a very large vertical velocity. And so the amount of time it takes to go from, vertical velocity to 0 velocity, it's going to take 0.2 seconds, okay? Okay. And so in the second situation, we're going to say that his legs give, okay? And so because of that, the amount of time that the body's giving itself to reduce its momentum is going to increase, okay? Okay. And so for this one, we're going to say the contact time is about 0.7 seconds, okay? Right, and so by him, letting his legs give when he hits the ground, it's going to grant him an additional ½ second of time to reduce his momentum to 0. Okay? And what we'll see is that it's going to have a big impact on, on the force that's being applied through his legs. Okay. Right. And so let's take these two situations and let's compute. Let's compute the muscle force in the quadriceps. As well as the joint reaction forces in the knee in order to achieve this change of momentum. Okay. Question, let's see. Question. So what does it mean to give and break the fall? Yeah, it's a good question. So, in the first situation, you can think of it as, when he falls down, his legs are just going to stay locked. And so you're basically just going to be a rigid object that falls and completely, and just hits the ground like that. And so when I say that the legs are going to give, what that means is that when the person contacts the ground with his legs, as soon as they make contact, he's going to let his legs kind of, bend and deform, right? And so, in a sense, they kind of bend along with the person falling, right? And so his feet are going to be on the ground, right? But before he comes to a complete stop, he's going to basically keep bending his knees until he can't anymore, okay? And so that amount of time that he's bending his knees as he's changing his momentum, that's what it means for his legs to give as he breaks the fall. Mm-hmm. Mm-hmm. Yep. Yeah, if you've ever gone rock climbing, actually, this is actually pretty terrible. So you don't want to land on your legs when you're rock climbing. So normally they tell you to land on your butt because your butt is actually a lot more cushioned, and it kind of does a little bit of this phenomenon as well as the fact that you're not putting your legs in danger when you fall on your butt. But you'll see that when you increase this contact time, it makes a big difference on the amount of strain that it puts on your body.
Is this kind of the same principle when people jump from a large height and then roll into their fall?
Mm-hmm.
Except it's extending contact time
Oh yeah.
Yep. And over a wider area.
Yep. Yeah. And so so when you roll, when you fall, then you kind of are also kind of doing that as well. Except you're kind of letting your whole body deform and kind of giving it's all about kind of giving your body more time to change its momentum. Yeah. Mm-hmm. Okay, so let's go ahead and jump into the calculations for this. And so just like the other linear dynamics problem with the hurdler, and so we're going to do this one in a few different stages. Okay. All right, and so the first thing we have to compute is we have to compute what the velocity of this person is right before he hits the ground. Okay. All right, and so for this, we're going to use our kinematic equation. Okay, so remember our kinematic equation is x is equal to x0 plus V0t plus 1/2 at squared. Okay. Right. And so from this, we can compute how long it's going to take for him to reach the ground. Okay. Because remember, this person is starting from a ledge that's 0.7 meters off the ground, and he's going to jump until he hits it, right? And so what we have from here is that we can plug in x is equal to 0.7 meters, okay? We're going to assume that we have no initial displacement. We're going to assume that we have no initial velocity, right? And so this person is basically jumping off from a standstill, okay? We know the acceleration due to gravity, and that's g, which is 9.8 meters per second square. Okay. We know 1/2, or at least, I hope we know 1/2. Right? Oh, question, why we wouldn't use the y version of this equation? Yeah, it's all the same. And so I just use x just because I always did, but you can substitute y in for x and it would be the same thing. All right, and so the only unknown that we have in this equation is t. So I think I just naturally, I kind of just use the general form of this kinematic equation. But I think the y version of this, they automatically plug in g for this. But I use this version with a, and then I just plug in g afterwards. Yeah. All right, and so if we solve for t here, we get t is equal to 2 times x divided by g. Okay. And so if we do that, we get 0.378 seconds. And so it's going to take him 0.87 seconds from the time he jumps off the ledge before he hits the ground, okay? And so we can compute velocity from this. Okay. And so we can use the other kinematic equation, velocity one, okay? And so our velocity here is going to be VO plus AT, okay? Once again, we're going to assume that we have no initial velocity, and so we're going to cross that one out, okay? A, we're going to plug in the acceleration due to gravity, G. And then for T, we just solve for it right there, okay? And so if we plug all those in, then what we get is a velocity of 3.7 meters per second, okay? And so right before he hits the ground, he's moving at a vertical velocity of 3.7 meters per second, okay? And so with that velocity, we can then use this to compute momentum, okay? And so momentum, remember, is just the product of the mass of the object multiplied by its velocity, okay? The mass was given to us in this problem, and so the mass is 60 kilograms, okay? And so we multiply that by 3.7 meters per second, then what we get is 222.24 kilograms meters per second. And so this is the amount of momentum that he has, right before he hits the ground. Okay. It's unfortunate, that we haven't come up with a better unit for momentum, but we just use the base units. Right? And so it's just going to be kilograms meters per second. Yeah. All right. Okay, and so that's how much momentum that he has. Okay, and so in order to stop this momentum, when the person hits the ground, then the normal force from the ground is going to apply an upward force to reduce this momentum. Okay, and so the next step is we're going to compute, the magnitude of that force that's needed to stop this momentum. Okay. All right, any questions on this? Okay. Okay. And so we're going to compute the normal force from the ground that's needed to stop this momentum, right? And so let's start with situation 1, right? And so in situation 1, remember the contact time for this one is 0.2 seconds. Okay. And so after he makes contact with the ground, his entire momentum is going to stop after 0.2 seconds. Okay. Okay. And so if we use our force impulse equation, right? So our force impulse equation is F times T is equal to mv2 minus mv1. Okay. And in fact, actually, we'll get there in a bit. Okay. And so, let's start with mv2 first, right? So mv2, that's the momentum of the object after the force has been applied, right? And so after the force has been applied, the body's going to come to a complete stop. Okay? And so the momentum in state 2, this is just going to be 0. Okay. And so all we're left with then is the momentum in the first state, which we just computed on the previous page. Okay. Okay. And I'm going to give it a negative sign here, okay, because our velocity is negative. Okay. And so, I'm just putting a sign there just to account for that. Okay. Okay. And so now we can take this equation and solve for F. Okay. And so we divide by T, where T on both sides is going to be 0.2 seconds. And so we get a normal force from the ground of 1,111.22 newtons. Right. All right. And so let's do the same for situation 2, where situation 2, remember the amount of time that we have is 0.7 seconds. Okay. And so we plug in T2 is equal to 0.7. We have basically the exact same formula. Okay. We get that F2 is equal to 317.5. Okay. Right. And so right away, you can see that the amount of force that's needed to stop the body is much lower when you let your legs give. Okay. Right. And so the next step that we're going to do is we're going to take this external force and then apply it onto an pseudostatic analysis to find out what's the forces in the knees and in the joints. Question. So the second velocity was canceled out because there was no secondary velocity. That's correct. Yes. And so after the forces are done being applied, then V2 is going to be equal to 0 because we're going to bring our body to a complete stop. Yeah. Mm-hmm. All right. Any other questions on this so far? Okay. All right. And so now let's take this internally and see what effect this is having on our knees. Okay. All right. So let me go ahead and draw a knee joint. Okay. Okay. So let's say this is our knee. Okay. All right. And so we have, first thing we have is our quadriceps muscle, right? And so we have an FM here. Okay. And for this problem, I'm going to define the muscle angle in terms of that angle right there. Okay. All right.
Relative to the horizontal.
Yeah, this one's going to be relative to the horizontal. Yeah. I'm just keeping it simple for this one, just to just kind of speed up our calculations. Okay. And then we have reaction forces at the joint that are Jx and Jy, okay? All right, and so I think we need a couple more pieces of information, okay? And so just to make some of the moments easier, I'm just going to give you directly the moment arm, okay? And so remember, the moment arm is just the perpendicular distance in between the force vector and the joint, okay? Right, and so the LM I'm going to give you is with respect to, this perpendicular distance right here, okay? And then same thing for the normal force, okay? And so for the normal force, the moment arm, I'm just going to give you this directly, okay? All right, and so LM, let's say LM is going to be 6 centimeters. Okay. And then let's say that LN, which is the moment arm for the normal force, let's say this is 9.5 centimeters. Okay. Okay. And so we don't take the angles into account here because I'm giving you the moment arms precisely. Okay. But if it was for the homework problem, or something like that, the ones that we've done in the past, you would have to take the angle into account if the lengths that I gave you are not the moment arm. Okay, right? Because traditionally, I would give you, what's the length of the leg, how far away from the joint is the muscle attaching from. Okay, but in this case, just to keep the formula simple, I'm just going to give you the moment arms exactly. Okay. All right, and so with that, we can go ahead and sum up the moments around the joint. Okay. Okay, so we have FMLM minus FN LN, okay, and this is going to be equal to 0. And so we solve this, we get FM is equal to FN times the ratio of LN over LM. Okay, so let's find out what FM is in situation 1, right? And so in situation 1, we're keeping our legs locked, and so the normal force from the ground is going to be much higher in this case, right? And so our muscle force in this case is going to be 1,759.43 newtons. Okay. Okay. Then we have situation 2. And so situation 2, remember, our legs are giving on us. Okay. And so that extends the amount of time that we're, that we have to stop our momentum. And so that reduces our force by a significant amount. Okay. And it also reduces the strain on your quadriceps as well. Okay. Oops. Okay. And so our muscle force in situation 2 is only going to be 502.71 newtons. Okay. Right. And so you can see it's a huge reduction, right? And so, half a second might not seem like that long a time, but, in terms of stopping your body's momentum, it can make, and this is like over 1/3, over 2/3 of a difference, right? And so I think situation 2 there, that's like almost 75% less force than situation 1. And so it's a really, really big difference.
It's like the difference between catastrophic injury.
Oh, for sure. Yep. 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 All right. And so, just because, we're a little bit short on time. And so, I'm not going to compute the joint reaction forces, but they kind of tell the same story, where situation 1, you're going to be putting a lot more strain, a lot more force on your joints. Situation 2, when you let your legs give, that's going to be a lot easier on your legs. Okay. And even better, if you land on your butt, right? So, and so you kind of, maybe take the contact first with your legs and then kind of, let your butt take the rest of it. That's probably one of the best ways to fall. Your caustics can take it, trust me. Your butt has a lot of padding, and so it helps a lot. All right. Any questions on this? No, no. Oh yeah, yeah. I've bruised my bottom when snowboarding too. I fall a lot there too. Okay. All right, and so before we move on, before we talk briefly about conservation of energy, I want to talk about impacts. Okay. And so impacts are nothing's really special about impacts. So impacts are basically the same thing as what we just talked about in terms of force impulse, but they're kind of a special case and where the contact times are really, really small. Okay? Okay. Right, and so because the contact time is really, really short, this results in usually very, very high forces. Okay. Right, and so because of these really high forces, impacts can be really, really dangerous to the human body, especially depending on where the impact occurs. Okay? Okay. And so, there's a lot of ways that, we can protect ourselves from impacts. Okay. And so, one big way is, if you notice a lot of safety equipment. Okay. And I think probably the best example of this would be, a lot of equipment for babies. Okay. Right, so babies are particularly at risk because their bodies are still very much developing. So their bones are very soft, and they're very prone to injury or malformation. Okay, and so almost universally, for anything that's designed for babies, that they're going to be impacting on, whether they're going to be walking on, crawling on, or potentially running their face into. A lot of that equipment is very soft and spongy, right? They all kind of share that same characteristics. Okay. And why is that, right? And so the benefit of having soft and spongy equipment is that they all have the goal of increasing this contact time. Okay. Okay. Right, and so let's say let's just do a very quick visual example, right? And so let's say that you have a baby, okay? Baby with a ginormous head, okay? And let's say that he's running around his house, as babies usually do, okay? And he's going to hit this table, right? Okay. But luckily for him, his parents thought ahead, and they put this protective layer of cushion on top, okay? And so normally, if that cushion wasn't there, and this baby just runs full speed ahead into this table, it's going to cause an injury because the table is hard, the baby's face is really hard, and so when two hard things impact each other, their contact time is really small, and so it's going to result in a large amount of force on the baby's head, which is not good. Okay, but because of the spongy equipment, before the baby actually kind of fully makes contact or fully changes its momentum, the foam is going to indent, right? And so the foam is going to do something like this. Okay. where the baby's face is like kind of right here. Right? And so because, because it takes time for that foam to kind of deform like that, right? And it may not seem like much. And so maybe you're only adding maybe 1/8 of a second, right? But that 1/8 of a second is actually critical. And so, any time that you can add to changing, any time that you add to change the momentum of an object, it makes really big differences on the amount of force that gets generated, okay? And so, it may not seem like a lot, but this extra time that it takes for this foam to deform, makes a big impact on the amount of forces that the baby experiences, okay? And so that's why, all baby equipment you see is really soft, so that it kind of, gives the baby more time to change its momentum. All right. Any questions on this? Yes, airbags work exactly the same way. All right, and so, before we close our chapter on linear dynamics, I do want to talk very briefly about energy. Okay. So I believe no discussion of linear dynamics is complete really without it. Okay. And so, I think we're all kind of familiar with the concept of energy, right? And so in order to perform any kind of work in the world, we have to expend energy to do it, okay? Okay. Right, and so there's several different forms of energy that we have. Okay, and so I'm just gonna go ahead and list them really quickly because a lot of these you've probably seen in previous classes before. Okay, and so on the one hand, we have work, where work is the product of force times distance. Okay, and so if you push an object, a certain distance with a certain amount of force, then you're performing work on that. Okay. Okay, we have kinetic energy, where kinetic energy is the energy that's associated with motion. Okay, and so kinetic energy is 1/2 mv squared. Okay. Right, another common form of energy that's talked about in classes is heat, right? And so heat is a thermal form of energy. Okay. Okay. We have potential energy, and we have several different kinds of potential energy. So potential energy is kind of an all-encompassing term for other things. Okay. And so one form of potential energy is gravitational potential energy. Okay. And so gravitational potential energy is just your mass times gravity times whatever height that you have off the ground. Okay. We also have spring potential energy. Okay, so that's 1/2 kx squared, right? And so that's the potential energy associated with the with elastic storage. And so this is the amount of energy that you could store up by stretching your muscles, right? Right? And so we talked about how muscles and tendons and ligaments are elastic structures. And so by stretching them beyond their normal length, then we can store up this kind of spring. This is basically spring energy inside the muscles. Okay. And there's way more than this. Okay. All right. And so the reason I bring this up is I kind of want to clear a little bit of a misconception with regards to energy and biomechanics. Okay. And I say misconception because it's it has to do with kind of how we account for calories. Okay. And so using formulas like this, it's kind of really easy to compute how much energy it would take to do a certain task. Right. And so as an example, Okay. Let's say that a person is going to climb, 40 flights of stairs or 40 steps. Okay. Okay. Each of these steps is going to be 25 centimeters high. Okay. And we'll say the person has a mass of 65 kilograms. Okay. And so with this information, we can compute the potential energy the person has, after they climb up those stairs. Okay. Okay. And so the potential energy is going to be the person's mass, which is 65 kilograms, okay, multiplied by gravity, which is 9.8 meters per second square. Okay. And then we're going to multiply by the height, where the height is going to be 40 steps times 0.25 meters per step. Okay. And so we compute this, and we get 6,370 joules of energy. Okay. Right. And so after this person climbs up those stairs, we say that he has 6,370 joules of potential energy. Okay. All right. And so there's no misconception with that part. And so that part's exact. Okay. Where the misconception comes in is, is in terms of, how much energy did the body actually expend to climb up those 40 steps. Okay. All right. Are there any questions on this before we talk about that? Okay. All right. And so, and I'll admit that I did this too when I first learned about energy, right? And so when I first learned about energy, I said that, oh, if I climb up these stairs, I can compute exactly how much energy that my body is expending. Okay. But unfortunately, it's not like that. Okay. And so in truth, your body actually needs to expend more. Yeah. Oh, yeah. The final answer was 6,370 joules. And so in truth, in order to perform a task like this, the body has to actually expend a lot more energy. Okay. Okay. Because if you compute it, right? If you perform the conversion, then this 6,370 joules, it might seem like a lot, but it's only about 1.52 calories. Okay. Which is not that much. And so you climb up 40 steps, right? You're gonna burn more than 1.52 calories. All right. And so the reason the body expends more energy than this is because the human body is a very kind of complex thing. Okay. And so there's factors such as you're not just using one muscle to perform this climbing, right? And so in order to perform a climbing motion, your body has to move a lot of muscles, a lot of which may not be directly involved with climbing up. Okay. Okay. And so some examples of some important muscles that are used is, maybe when you're walking up the stairs, you're swinging your arms, right? And so when you're swinging your arms, that's going to expend some energy. Okay. Your body needs to maintain balance the whole time. And so your body needs to make sure that you don't just completely topple over. Okay. And so you have your core muscles and your back muscles that are contracting to make sure that you stay balanced throughout the entire climb. Okay. And even in your legs too, right? And so, I think it's, it's easy to think that maybe we're only using our quadricep muscles to go up, right? But your body has to control that motion as well. And so even the opposing muscles from the quadriceps, which are your hamstrings, that's also acting to kind of control the motion, right? And so you have a little bit of agonist and antagonist motion going on at the same time. Yeah. Some hip too, yeah, absolutely, yeah. So there's going to be some hip action as well. Yeah. And so it's it may seem like a simple task of just stepping up a stair, but your body's doing a lot more other stuff as well. Okay.
You get a lot of good activation.
Oh, I'm sure, positive, yeah. Okay. And there's also, some energy losses in the system too, right? And so it's not going to be a perfectly efficient system, right? And so in order for your body to move, like your muscle has to transport energy to your limbs, and your limbs are going to slide past each other, right? And so there's going to be some frictional losses. There's going to be some inefficiencies in the system, okay? Okay. And there's also, some metabolic limitations too, right? And so, not all of the energy that you consumed is perfectly converted to, to motion, right? And so there's some inefficiencies in the metabolics of the process too. Right? And so if you drink like a soda, right? So not all 700 bajillion grams of sugar in that soda is going to go towards you, moving, right? There's going to be some losses in that process as well. Okay. And in fact, the inefficiencies in the system are pretty large. And as such, it's to the point where only about 25% of the energy consumed by muscles is actually converted to mechanical work. Okay. Okay. And even this number too, this 25% is a very, it's an average, but it's an average with a huge variance too. Okay. And so, don't look at this number and just multiply the above one by 4 and say that's the amount of energy that my body's expending, because it depends on a lot of other factors too. Question. So what I say that incline walking is almost equivalent to stairs when it comes to muscle usage, like if you compare two slopes and they're the same. That's a great question. That's a really good question, actually, because maybe you use the same muscles when you're climbing a slope versus stairs, but the way that you actually use the muscles are different in those two cases, right? And so when you climb up a stair, it's a much quicker motion, right? And so you kind of step on the stair and then you kind of push up in kind of one big kind of thrust, right? Versus when you're walking up a slope, it's much more gradual, right? And so you apply, a larger, maybe a smaller force, but over a longer period of time. And so, whether one's more efficient in terms of energy than the other one, it's hard to say because it depends on a lot of different factors. But they are very different motions for your body. Right? All right, question. So is that to keep our body's temperature? Yeah. So some of that energy is going towards temperature control as well. Yeah, for sure. Yep. Yep. And so actually, for most devices, I know a lot of people have smartwatches nowadays, or they have apps on their phone that keeps track of the amount of calories that you burn. That's a very, 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 very rough approximation. And so, I wouldn't put too much stock into how much calories your iWatch is saying that you burn, because it's, if you want to be really accurate about that stuff, you need a lot more sensors of how your metabolism is doing and stuff like that.
I think I was actually watching a video about that recently. And apparently there was like a meta-analysis or something like that that showed that those watches can overestimate your calories by as much as like 40%.
Oh, yeah.
In some cases.
Oh, yeah.
And that like the only way to like truly know how many calories that you burn is to do like a watt calculation.
Mhm.
Apparently.
Mhm.
But to do that, like you have to be riding something that you can put a watt meter on.
Yes.
You can't put it on a tread. Like basically it's a bike only. It's
Yeah.
the only way to know exactly how many calories you burn.
Mhm.
Because like a mechanical system, so that's the only way you can read the energy output.
Yeah. Yeah.
Which sucks, because then you never really know how many calories you're burning.
Yeah, it's a hard process. And so, yeah, it depends, you need to have a very controlled, laboratory setup. So a bike is great because it's, every ounce of energy that you expend, it basically gets transported to the bike. And so there's not really your body's not really doing much else other than riding that bike. And so that makes a lot of sense. But even, with that laboratory setup, there's still stuff that's going on in the body that's really hard to really quantify as well. So yeah, it's really, it's hard, which is really interesting because it's, I think a lot of people make decisions in their lives based on that. So it's, just kind of keep that in mind. And so, I'm not saying that those calorie counters are not useful. And so I think they're useful in the sense of quantifying maybe how much work that you did. Maybe saying that, I worked a little bit harder in this workout today versus the other one. And so it's definitely useful for that. But in terms of actually counting, say, I burned exactly, I don't know, 200 calories today, I wouldn't trust that all too much. All right, any final questions on this before we move on to angular motion? Okay. All right, so let's start talking about rotational motion. So we have about 15 minutes left in class. I think we can get a good start on this. All right. And so in terms of, of usefulness to actually quantify human movement, I would say rotational dynamics are a lot more useful, okay? And so there's a lot that we can do with linear dynamics, right? And so we kind of just got done talking about that. But rotational dynamics is really when you start to kind of dive into the nitty-gritty of actual limb motion, okay? And the big reason for that is, the way that our body segments move, they're almost entirely rotational motion, okay? A lot of the joints in our bodies, at least the major joints that we consider as kind of our joints of movement, have some kind of hinge motion to some degree, right? And so some are just kind of a straight up hinge, like our elbow joint is just a straight up hinge. Maybe we have a ball and socket joint like our shoulder, okay? We have very few joints in the body where we actually have kind of linear sliding motion, and most of those are just in your hands and your feet, okay? And so if you want to do any kind of, real kind of a dynamic analysis of how the body moves, we need to talk about rotational motion, okay? And so let me just draw maybe an elbow here. Okay. And so if we want to quantify, how quickly you're kind of moving your arm up, we need to talk about it in terms of, what its angular velocity is, okay? Right. Really, we're limited in dynamic situations without angular motion, okay? All right. And so that's kind of why we need, angular motion. So, we're going to do a lot of review of, what are angular kinematics, what are angular dynamics. And so we'll spend quite a bit of time with angular momentum. And then we'll actually do some calculations of how you can quantify this stuff. Okay. And ultimately, it's going to lead up to a technique known as inverse dynamics analysis. Have you guys done inverse dynamics analysis in a previous class before? Okay, that's cool. So it'll be a new thing. Right? And so the way inverse dynamics works is that you can take a motion, right? And so imagine that you have someone working in a sports lab, right? Or maybe you put on a motion capture suit, and so mocap suits are becoming a much cooler thing nowadays. Okay, and what you can do with those mocap suits is you can actually, or with high-speed cameras, you can quantify how quickly or how much angular velocity your arms are giving as they rotate. Okay, and then based on that data, you can compute in a very systematic way how much force and how much work your muscles are expending to produce that motion. Okay. Okay. And so you'll be surprised, inverse dynamics, it has a fancy name and I'll admit it's a little bit of a lengthy calculation, but it's cool because you can get really detailed, information about, what your muscles are doing on the inside. Okay? And so in the textbook, actually, the textbook actually showed results from a study that did inverse dynamics analysis on baseball players, right? And so they did, they really did a really detailed motion capture of baseball pitchers, throwing a baseball, and they were able to quantify, how much work is the biceps muscle doing, how much is your shoulder doing. Yeah. Mm-hmm. Our question: so do they use thermal cams, like observing muscles that get warm as it moves? I'm sure they do, and so there's some variations in this that combine kind of a thermal cam, which shows how hot the muscles are getting as it's working as well. So yeah, so there's definitely lots of variations of it. And so we'll work our way up there. And actually, I was planning on giving you an inverse dynamics analysis, maybe a simple one for the homework, because it's it is pretty cool, and I think it's one of the unique outcomes from biomechanics that you may not see in a traditional dynamics class. All right, but we'll work our way up there, and so that'll be kind of at the end of this unit. Okay. All right, so before I do that, are there any questions on this? Okay. All right, so let's start at the very beginning. So let's talk about just angles and how we measure them in a body. Okay. Okay. And so let's define angle. Right? I feel like angles is something that we use in math like forever, but I don't know if an exact definition of it is given. Okay. But the way I define angle is that it's a quantity that kind of roughly describes the orientation of one segment to another. Okay. Okay. And so, with this definition, it's useful to just basically take this description of the human body as a collection of segments. Okay. And so we're going to have like a stick man representation. Okay. And so if we represent each of the body segments as a line segment, right? And so let's say that, this one in the middle here is our torso, and then we have our two arms and our two legs, okay? What we can do is that we can measure the orientation of one body part to another with an angle, right? And so, depending on what angle, so that's your left wrist, I guess, okay? And so depending on the orientation between your wrist and your arm, we can measure that with an angle, right? And so whether your wrist is like this, or whether your wrist is like this, right? And so those are going to make different angles with respect to your forearm. Okay. We can do the same thing with all the other parts, right? And so let's say this is theta 2. Okay, and so that's your forearm relative to your upper arm. Okay. Okay, then we have theta 3, right? We go to the legs. This is theta 4, theta 5. Okay. Right. And so angles like this are used to quantify, how one body part is measured relative to the other. Okay. And so this is kind of how, doctors and clinicians used to say that, your body is in one configuration versus another. Okay. So one way that you can describe that is through all of these body angles. Okay. All right. And so, we talked on the previous page about motion capture technology, right, or mocap technology, or even just with high-speed cameras, right? And so, whenever you want to quantify the movement of a person's body, one thing you can do is you can kind of overlay lines like this onto their body segments and track how those body segments move as a function of time. Okay. Yeah.
So this almost like breaking down, is this almost like a kinematics of mechanisms type approach where you're breaking the body down into really simple mechanisms and then just measuring how the angle is changing?
Exactly. Yep. It's exactly the same as that. Yep. Yep. So this is so the comment was this is exactly the same as you would, or this is the exact same approach that you would take in kinematics of mechanisms. And so it's the exact same thing. Okay. All right. Any questions on this? Okay. All right. And so you can measure angles like this with with very high technology, right? But you can also measure this stuff with some more simple measurement tools too. Okay. And so one measurement device that doctors have in their office is something called the Goinometer. And so Gynometer is it's basically a big protractor that's used by doctors to measure body angles. Okay. Okay. And so let's say that you're going to use a Gynometer to measure the body angle of an elbow joint. Okay. Right. And so visually it looks something like this. Right? And so there's going to be an arm that goes like this that you align with one limb. There's another arm that goes like that, which you align with the other limb. Okay. And then you have a device like this, okay, which is essentially a protractor. And then the body angle can be read just straight off the Gynometer, just like that. Okay. Right. And so the way that you use this is that all the Gynometers have a kind of a central piece right here. Okay. And so you need to align that center with the joint, exactly with the joint. Okay. Right. So for a normal person, this is actually pretty difficult to do. And so, you might think that, you might think, where your center of rotation is for your elbow, but there's some uncertainty as to where you can actually put it. And so the only person that can really use this really well is usually a trained clinician, because even if you're off center by just a little bit, that's going to change the body angle that it's measured, pretty significantly. Okay. Okay. And so any kind of trusted measurement, has to come basically from a clinician. Okay. All right. And so the last thing I want to go over, before we wrap it up for the week, is the idea of angular velocity. And so angular velocity is basically the angular equivalent of regular velocity. Okay. But remember, the definition for regular velocity that we had before was a change in position over time. And angular velocity is defined as a change in angular position over time. Okay. And so the symbol that we usually give for angular velocity is omega, and it's going to be the derivative of theta over time. And so it's d theta dt. Okay. It would be nice if the equipment came with an X-ray. Yeah. So X-rays normally are difficult to do because it involves radiation, and so you have to be kind of really careful about how you use X-rays, because it's you usually need a trained tech in order to do that. Yeah. All right. Any final questions on this before we wrap it up for the week? Okay. All right. And so we'll leave it off on there. And so next week, next week, of course, is our midterm. And so Monday we'll continue on with rotational motion, and then Wednesday we'll take our midterm. Okay. So thank you guys for tuning in this week. Thank you guys for coming in, and I'll see you guys next week. And I promise I'll make the next homework, the last homework, shorter than this one, because I know the last two homeworks have been pretty long. So last homework will be shorter. I am. So I'm gonna record that on Friday. Yeah. So please vote in the poll. Oh yeah. So please vote in the poll to tell me which topics you want, and then I will record the video on Friday. Yeah. What were you saying, Jacob? Oh yeah. Yes.
I'm gonna go talk to Dr. Weiss about one more quick question I know about the homework.
Uh-huh.
So I may be a minute or two late, just because I'm gonna have to run between buildings. So I'm just letting you know.
Okay. Yeah. No problem. Yep. No problem. See ya. Have a good weekend. Yeah, that'd be great. Was this the page you wanted to see, Carlos?
But can you explain, like, I'm always stuck with the bag one, like I can't find the moment for the bag.
Yeah, for sure. So I explained this. So the full explanation you can watch the video for, because I can't stick around too long because I have another class after this.
Oh, I'm sorry.
But basically, the way that you compute this moment arm is because the backpack is a vertical force like this. And so the moment arm between the joint and the force is going to be this horizontal distance in between them, right? And so the
Right.
way that you compute that distance is you kind of break up this length into two different triangles. And so the first triangle that you have is with respect to the angle theta, right?
Mhm.
And so you can compute this horizontal length right here by doing the length of this hypotenuse multiplied by cosine theta.
Okay.
And I mentioned I forgot to give you one length in the problem, is that this length right here, the backpack acts halfway up the spine.
Oh, I see.
Yeah, so I just noticed today that that's missing as a crucial piece of information. And so once you have this as LT divided by 2, then you can say that that horizontal length is LT divided by 2 times cosine
Cosine
theta.
theta.
Right? And then I think the tricky part is factoring in this LB right here, right?
Mhm.
And so you can once again kind of draw a triangle, okay? But this time the angle theta is going to be on this part right here.
Mhm.
So this horizontal length here is going to be LB times sine of theta, right? And so if you take the difference in between these two lengths, we do LT divided by 2 cosine theta
Mhm.
minus LB sine theta. That's going to give you your moment arm for the.
All right. Thank you so much.
Yep, no problem. Yep, I gave a little bit of a lengthier description at the beginning. So if you watch the lecture video once it's posted,
Yeah.
then you can see that. Yeah.
Okay. Thank you.
Yep. Mhm.
Have a good one.
You too.